right, so in this video, we're going to be looking at why we write equilibrium expressions, and we're going to use Ka, acid dissociation constant, as our example. So here's the situation. If you have a strong acid, right? For example, HCl. HCl is a strong acid. That's a little bit too small. So let's change that. Here, this should be. So HCl is a strong acid, right? Now, when HCl dissociates, notice the arrow that we're using here. This is a fully dissociation arrow. So it's going to completion. It completely changes the H plus ions and chloride ions on the right hand side. Okay, so this is a full dissociation. If the concentration of the hydrochloric acid was 0.1 molar, we're just choosing any random number now, then we could say, because it completely dissociates, that the concentration of the proton here is 0.1 molar. And since this is a 1-to-1 ratio, if the concentration of the acid is 0.1 molar, then the concentration of the chloride is also 0.1 molar. No. So we can simply quantify the number of protons here. And if we were to calculate the pH of the substance, now we could say pH is equal to the negative log of H plus ion concentration, which we would get from the dissociation of the strong acid. Similarly, if you have a strong base, such as sodium hydroxide, right? You dissolve it in water, it goes to completion. So full ionization. So you're going to get the sodium ions and the OH ions, right? That's what you're going to be getting here. Now, if the concentration of this is a O, if the concentration of the sodium hydroxide is again 0.1 molars, then the concentration of the OH is 0.1 molar, right? Yes, so the concentration of the OH is going to be 0.1 because of the full ionization of the sodium hydroxide. Now, we know that pH plus POH is equal to 14. So if you know this, then you could clearly find the pH of the substance. And if they ask you to find so you could find the pH, and if it is that they're asking you to find the H plus ion concentration, of course you find the pH and then find the H plus ion concentration from that. So that's the deal with the species which are strong acids, strong bases. They fully ionize, and so you can easily determine the OH ion concentration. You can easily determine the H plus ion concentration from that. Now the question is, what if the substance is a weak acid or a weak base? How do you quantify H plus ion concentration? So that's what we're really going to look at right now. So let's say you have a weak acid like my color right there, yeah. You have a weak acid like ethanoic acid, CH3COOH. It dissociates. Now the first thing is you're using these reversible arrows because it's a weak acid. And so you end up with the ethanoate ion plus the proton over there, right? So this is a weak acid. The question now is, what's the concentration of the H plus ion? Let's say you start with 0.1 molar of ethanoic acid. Now, because of the nature of this reaction, you can't say for certain that the concentration of the acid over here is 0.1 molar because it's a weak acid. And what that means is, first of all, the ethanoic acid doesn't fully ionize. So not all of the ions would be separated. So that's one thing. The next thing is that it's a reversible reaction. And this base, this conjugate base, is a strong conjugate base. So once it is formed, it's going to combine with these protons to reform this species over here. Okay, so you can't say for certain how much H plus ion is present at a given time, or ethanoate ions. But because it's a weak acid, you can reasonably assume that the amount of dissociation which occurs, so the concentration there is zero point 0.1 and the dissociation is X, you can reasonably assume that the amount of dissociation is almost negligible. It's almost zero. So the concentration of the acid remains relatively constant. Okay, you can assume that. So that's the first part of the thing. Now, to find the concentration of the H plus ions and the ethanoate ion over here, what you're going to have to do is write a acid dissociation constant. So let me just clear this off right here now and write the acid dissociation constant. So that now the equilibrium constant, and since it's an acid, this becomes an acid dissociation constant. So it is Ka, which is going to be now equal to the concentration of that, the product of the concentration of the products, times the product of the concentration of the reactant, which is this. Okay, so there you go. Right? And so this is your equilibrium expression. And of course, this Ka tells you the extent of the reaction, which we would say, or it tells you which side you have more stuff off, pretty much. In other words, do I have more products or do I have more reactants? Now, you have to think about this like a ratio, which it is a ratio. How much of the product do you have divided by how much of the reactants? If Ka is 1, for example, okay, it means that the numerator divided by the denominator is equal to 1, which means that they are the same. Good. If it is that Ka is 2, it means that the numerator, which is up here, divided by the denominator is equal to 2, which means that the number at the top is twice as much as the number at the bottom, which means that the amount of this and the amount of this, let me change the color there, the amount of these two species, right, is twice as much as this down here, which means that the reaction is pushing towards the right-hand side. That's the direction it's going in. If it's 3 times the amount, same thing. It's 3 times. Now, what if it was negative? Let's say it was -5, right? If this is -5, for example, or minus 10 to the -5, let's put it 10 to the -5. If Ka is 10 to the -5, then what this means is that you have 1 divided by 10 to the 5, which is what? 5 zeros? 5 zeros. 1 over, how much is that? 10,000. 1 over 10,000, which means that you have 10,000 of this and only 1 of these two things up here, which clearly shows, if you look at it, that the amount of ethanoic acid far supersedes the amount of ethanoate ion and protons, which means that you pretty much almost have zero dissociation, right? And that tells you whether or not the reaction is leaning towards the right or to the left or vice versa or whatever the case might be, simply by looking at the Ka value. Now, this number 10 to the -5, 1 times 10 to the -5 is a very small number. And to make it more manageable, I'll erase all of this now. To make it a more manageable number, we decide to change it to a logarithmic number. Okay, so we put it on a log scale. So we find what we call the pKa. So if I were to find the log of this number, I would end up with -5. However, if I were to do the negative log of the Ka, I would end up with 5, which is a much easier number to understand. You see, 5 is easier to work with than -5, and it's even easier to work with -5 versus 10 to the -5. Right, so what we have done really basically is change our Ka values to pKa values for them to be more easily understood. But remember, the pKa is coming from the Ka ultimately. All right, and so this really is the idea behind equilibrium constants and acid dissociation constant, and the same thing for the base dissociation constant for weak bases. And so, of course, from your Ka, you can find the concentration of the proton, you can find the concentration of the ethanoate ion, and you can do your gymnastics there to find whatever it is that you're looking for. All right, so I hope this was helpful in understanding where your pKa comes from, what your Ka value, what it means, what does the Ka value mean, etc., and why we use a expression to calculate H plus ion concentration and to get a Ka value. Why are we doing that really? All right, so all the best, and I'll see you guys next time.